Thank you, and thanks to the organizers for inviting me to speak here today. Before I sort of explain what I mean by partitions into values of a polynomial, let's start with the definition of partitions just to make sure that everyone is on the same page. So a partition is just a way of writing a number as a sum of other integers. And we call the summands, we call them parts, and we're interested in counting certain partitions, so we have a notation P of n for the number of partitions of n. So for example, there are 5 ways to write 4 as a sum of integers, as listed here. And there are lots of cases where it's interesting to look at different partition functions where you restrict what you're allowing as parts. So instead of allowing all the numbers, we might partition into only odd numbers, in which case there would only be 2 partitions of 4. Or we might look at only squares or prime numbers, things like this. So what I'm interested in is I'm going to set I'm going to restrict the set of allowable parts to be the values, the sequence of values of some polynomial where you plug in integers into the polynomial, and then that's going to be the set that I'm partitioning by. So sort of as a jumping off point, I'd like to use partitions into kth powers, which is something that's been studied before. So we're going to fix a power, and pk of n will denote the number of partitions where all of the parts are perfect kth powers. So if we fixed k equals 2, then we have 4 ways to partition 10 into squares. And just as an example, if we fixed k equal to 3, then there would be 7 ways to partition 35 into cubes. And so those who are familiar with Waring's problem, this might look a little bit like Waring's problem, except that I'm not restricting how many parts. So in Waring's problem, you would be looking at a sum of 5 squares, or a sum of, say, 12 cubes or something. And I don't care how many parts I have in my partition. I can have 100 parts, and that's OK. So let's look at some of the history and background of this problem. It starts with Hardy and Ramanujan, as most partition problems do. So in 1918, Hardy and Ramanujan were studying the partition function, and they introduced the circle method to show an asymptotic formula for the number of partitions of n, and it's equivalent to this asymptotic, it has this asymptotic growth as the main term. And in that paper, they stated a lot of other problems that could be solved using their new method. And one of the problems that they mentioned was partitions into kth powers. And so they claimed without proof this asymptotic growth for log of pk of n, where you're looking at the partitions into perfect kth powers. And it looks sort of like a mess, but all of this is just a computable constant that just depends on k. And since we're fixing k in advance, then we're just saying that log pk of n behaves like some constant times n to the 1 over k plus 1. And actually, if you look at just p of n and you took the logarithm of this expression, you would end up with a constant times n to the 1/2. And if you plugged in k equals 1 to this expression here, it's exactly the same constant that you would get. So so this was claimed in 1918, and they did not prove this. But in 1934, Wright published a paper where he did actually write an explicit asymptotic formula for pk of n. And his paper is a bit of a monster. It's over 50 pages long, and it includes only this one result. So it's basically just the proof of this result of pk of n. And even to state the formula itself, you need to introduce some new strange objects called generalized Bessel functions, which are rather esoteric these days. And so in 2014, Vaughan revisited the problem and found a much simpler way to solve the problem for this partitions into squares. And he still maintains a decent error term, but his paper is maybe 12 pages, so quite an improvement there. And so, and he's only looking at the square case, and so I've generalized that to kth powers. And so here is the asymptotic formula for partitions into kth powers. And we have, So if you just look at the main term is it's this exponent of this constant times x to the 1 over k. X is something that depends on n. I needed to use x and y just to fit it on one slide so that I could, anyways. But then you just have these multiplicative error terms that you actually can get arbitrarily. You can get an arbitrary power of y saving here. But I'm mainly interested in the growth of log pk of n for this talk. So if we take the logarithm of this, then all of these multiplicative terms become additive terms, and they go into the error term, and we're just left with exactly what Hardy and Ramanujan claimed. So this is sort of like where I'd like to start, that we have this result for, we know how many partitions there are into kth powers, and I'd like to see how can I generalize this where instead of using polynomial values of x to the k, can I use some other polynomial? So what I'm going to do is I'm going to fix a polynomial. And I'm going to write it just in terms of its leading coefficient and the roots. And then we'll say, OK, so the set of parts that I'm allowing is where does this polynomial land on the integers? And in order for this to make sense, so I'm going to look at pf of n, which is the number of partitions whose parts are all integer values of this polynomial. And in order for this to make sense as a problem involving integer partitions, I need some restrictions on my polynomial. So first of all, I want my polynomial to be integer valued. I don't need integer coefficients or integer roots or anything like that. But if I'm talking about some restriction on integer partitions, then I want to make sure that whenever I plug an integer into my polynomial, I get an integer back out. Otherwise, we're doing something more generalized, which is not really integer partitions anymore. The second is just that I want to make sure I don't have any common factor here. Because, for example, if I use the polynomial x squared plus x, then that always takes on only even values. And it would be kind of hard to partition, say, 17 into values of my polynomial. So I just want to make sure that I can partition every number into values of the polynomial. And then this last restriction, that the roots don't have real part greater than or equal to 1, that's a more technical condition that's needed in parts of the proof. But one nice thing that it makes sure that we have is that I want to make sure that this set that I don't have any roots of my polynomial on the positive real line, because then I might have, say, 1 and -1 in my set, in which case I could just keep adding 1 and -1 and end up with infinitely many partitions. So to keep everything finite, we're going to have this restriction there. And so then the goal is to find an asymptotic formula for pf of n for general polynomial n. And I call this a goal because this is definitely work in progress, and I have not solved this problem for all polynomials or even for any really large class of polynomials except for x to the k. But I have some ideas of what the main term should be, and so that's what I'm going to talk about today. So just before we get to anything, let's talk about just an example so we make sure that everyone understands sort of what all my restrictions are and everything. So we have if we look at this polynomial, this is not an integer polynomial, but it satisfies all the requirements that I said. And this is the polynomial that generates the triangle numbers. So if we're partitioning into triangle numbers, then we can see just as an example that there are 7 ways to partition 10 if I'm only allowed triangle numbers. And so the goal would be to have some asymptotic formula that you could plug in any polynomial, and you would see how many partitions there are into that sequence of values of that polynomial. And I use triangle numbers just to say that there are other interesting sequences that do have polynomial generating functions. OK, so here's some special cases that are known. So I already talked about Vaughn's work on partitions into squares. And so this is the formula that you get for partitions into squares. And then if you generalize that to kth powers, then you end up with this result that I mentioned a few slides ago. And then there's one other result of Bernd, Malik, and Zaharescu. I put 2017 here optimistically. It's in the pipeline, and it's been submitted, and they're waiting for it to be published. But so we'll say optimistically 2017. It'll come out sometime. But they looked at partitions into powers in a certain residue class. And so that corresponds to using the polynomial bx plus a to some power. So instead of using perfect powers, you're taking some linear polynomial to a power, and of course we need to require that a and b be relatively prime so that we don't have any common factors. And so their result, they actually have an explicit asymptotic formula, but if you just take the logarithm and look at the asymptotic growth there, then you end up with this, which, if you notice, is almost exactly the same as the kth powers case, except that we have this extra little b here, which is the same as the leading term. It's actually the kth root of the leading term, a leading coefficient of the polynomial. And so what this sort of hints at is that this main term of the log of these log of the number of partitions into the polynomial depends only on the degree, and quite heavily on the degree, and then a little bit depends on the leading coefficient, but that none of the other roots or other coefficients of the polynomial seem to matter, at least in the main term case. And so from these three cases, we have this claim, which this is, I say it as a claim because I've not worked out how all the error terms work. I've gone through the argument ignoring error terms and making sure that all of the main terms work out the way they should be. So this is my prediction of what the main term will be of log pf of n for any general polynomial. And you can see that we have this same constant as we had for the kth powers case, and that the only thing is that we're basically scaling n by the leading coefficient of our polynomial. And so if you want to think of that in a concrete example, it's saying that the number of partitions into triangle numbers of partitions of n into triangle numbers is roughly the same as the number of partitions of 2n into squares. And if you think of, triangle, like a triangle number is roughly 1/2 of x squared, right? So that sort of makes sense, because if you're partitioning into squares, you're basically doubling every part, which is going to be a partition of 2n into squares, where you had a partition of n into triangle numbers. Roughly in main term, dominating term terminology. Okay, so now I'd like to go into a little bit of the proof of how the kth powers case works and how things would work in general for general polynomials if everything works out the same. So we have we start with the generating function. So the generating function for partitions is given by this product of geometric series. And if you haven't seen this generating function before, then it's actually a really easy exercise to sort of work out why this is the generating function for partitions if you just sort of write each of these terms as a geometric series and then write out the product, like sort of distribute all of the terms. Then you end up seeing that the coefficient of z to the n is going to be exactly the number of partitions of n. And if you go through that exercise, you'll see that if you want to restrict to some subset of the integers, then instead of taking a product over all n, then you're just going to take a product over the set that you're allowing as your parts. And so from that, you can immediately see that the generating function for pf of n is given by this infinite product here. And now that we have a generating function, we can use Cauchy's theorem to extract the nth coefficient. And so we see that pf of n is given by this integral, which is Cauchy's theorem just written in polar coordinates. Okay, so I have my generating function, which is this infinite product. And then I need to solve this integral that has this product in it. And I much prefer to play around with integrals and sums rather than integrals and products. So I'm going to take the logarithm of my generating function, and then I end up with this double sum, which, I don't know, for me is much more easy to deal with. And you can sort of see in this double sum that we sort of have almost a zeta function showing up that will show up later in the proof that we end up with. And So now I've changed the problem a little bit. Instead of having psi of f of z, I have this exponent of this double sum here. And so this is what I need to work with. And so the main tool that I'm using for most of this is the Hardy-Littlewood circle method. And so I'll just give a brief overview of how this works. Is that the critical step is we're going to need to consider exponential sums of this form. And the key idea is that if theta, which is sort of my multiplier here in front of my polynomial, if theta is close to a rational number with small denominator, then we have good estimates for this exponential sum, and that is going to be the main contribution to this integrand. And if it's sort of far away from a rational number with small denominator, then it's going to be put into the error term, and that's what we call the minor arcs. And so traditionally, you decide what you want to mean by close and small and good, and then you define your major arcs that way, and all of your major arcs will contribute to the main term, and then all of your minor arcs you just sort of bound uniformly and put into the sort of sweep them under the rug into the error term, which is somewhat difficult to do sometimes, but that's how it works. But in this case, actually, the main term, the major arc at the origin is much, much larger than the contribution from the major arc at the origin is much larger than any of the other major arcs. So that my main term comes only from this major arc at the origin. And all of the other major arcs I just bound and put into the error term. And I still treat them the way I traditionally would treat major arcs. The estimates and I still use the estimates that I would otherwise use on these exponential sums the way you would traditionally handle major arcs. But then I just say, okay, well, that is smaller than what I needed it to be, and so I'm just going to put it into the error term. And then the minor arcs I treat the way you would traditionally treat minor arcs, and they're also error terms. But my entire main term of my asymptotic formula is coming from just this major arc at the origin. And so just really close to 0 is where, or really close to 1, I guess, depending on whether you're thinking of it as a circle or an interval, is where I'm concentrating most of my efforts. And so let's look a little bit at what happens right at the origin. So I call these main term heuristics. So if you plug in x to the k for f of x, then everything works exactly as I'm saying. If you plug in some other polynomial, then if you ignore error terms, everything works exactly as I'm saying, but I haven't, just full disclosure, I haven't actually worked out to make sure that the Hardy-Littlewood method works, still works, and I might need some more delicate work there. But so if you have this polynomial, f of x, then we're looking at this logarithm of the generating function, and this is what shows up in the integrand. And I need to estimate this in order to work with my integral. And so what I'm going to do is I'm going to take a Mellin transform. And the Mellin transform is going to basically turn estimating this into solving a residue integral. And so the main contribution to Pf of n is going to come from computing the residues of this object here, which is what comes out of the Mellin transform. Don't worry about what m is. It's just some big ugly thing that I condensed because we don't need it here. So we have gamma and zeta, and then some constant to the s, and then this strange Dirichlet series, which if you're working with x to the k is actually just zeta of ks. But if you have some other polynomial, then it's sometimes called a polynomial zeta function, and it's sometimes called a Dirichlet series associated to a polynomial. But in any case, it's been studied, and we know what the analytic continuation is and what the residue is at certain poles. And so the dominant singularity of this integrand is going to be a simple pole at s equals 1 over k. All of these first terms are analytic at 1 over k, and this is the rightmost pole of this Dirichlet series, appears at 1 over k. And the residue there is given by 1 over k times the leading coefficient the kth root of the leading coefficient. Okay, and so the residue of the entire integrand, of course, would be this, and then you plug in 1 over k to the rest of the expression. Okay, so with this residue in mind, and knowing that the main term needs to be dominated by this rightmost singularity, then let's look again at the special cases that are known. So I've color-coded this to sort of keep track of where the residue is appearing. So if we have our polynomial with leading term a, and we have k roots, then we see that the degree shows up there, and then the kth root of the leading coefficient. So if we look at powers, where our leading coefficient is 1 and our degree is k, then we have this residue appearing right here in this constant. And if we look at the powers in a residue class where we do have an actual leading coefficient, then we also see the residue appearing right here in this part of the constant. And okay, so we only have 2 cases, and that might look sort of like a coincidence, but if you go through and if you go through the argument of where this expression actually comes from, then you'll see that actually this is exactly where the residue is showing up in the argument, and so that gives the like sort of justification for this claim that you have. And I moved it because I had a kth root of the leading coefficient here and then a kth power. So I moved it over here to make it more clear that it's really just scaling the number that you're partitioning. And so then we have this. This should be the main term of the kth of the polynomial partitions into any polynomial. Okay, so sort of as a few last remarks, I'll say something about what if we wanted. So okay, so this is definitely true for kth powers, and I predict that this is the main term for any polynomial. So, but what can we actually prove is where the obstacle is going to come up. So these heuristics predict that the main term of log pf of n should depend only on the degree and the leading coefficient of our polynomial. Now, if I wanted an actual full asymptotic formula, then that would depend on all of the roots of f, and all of those would come up. And if you look at Barrett, Malik, and Zaharescu's result about partitions into a certain residue, powers of a residue class, then you do see that that other root, or the root of the polynomial, which is a over b, right? Because they had, I don't have chalk, but oh, it's over here. So they're looking at f of x. I don't know if you can see that. There we go. F of x equals, I think I wrote it as bx plus a to the k. And so you can rewrite this as b to the k times x plus a over b to the k. And so you have your roots a over b, and they do have, I think they call it alpha in their paper. They do have this showing up repeatedly in their asymptotic formula. So it does actually depend on all the roots of f. Oops. There's nothing there. And the way that it's encoded is we need to study this analytic continuation of these Dirichlet series associated with polynomials. And these are well studied. We know that the roots of this, or the poles of this look something like 1 over k, or they look sort of like m over k, where m is less than 1. So you have less than or equal to 1. So these are the poles of ZF of S. So the poles of Z of S look like M over K, where M is less than or equal to 1, potential poles, because some of them, you might not have poles everywhere, but the integrand at least will have at most simple poles at these values. And so once you sort of deal with the residues and the poles of this, then you can sort of plug that in to the Hardy-Littlewood method arguments, but it will be delicate and would probably need to be split up into several different cases, depending on the degree and on what assumptions you have about the roots. So I might need to make some more, in order to actually prove this claim, I might need to make some more strict assumptions about what polynomials I'm going to use and split it up into cases that way. But I will stop there, and thank you. Yeah.
Do you have any intuition as to why the term near 1 is just so much bigger than the others? As far as I know, that doesn't happen in like the original.
Yeah. Okay, so let me go back to the actual formula. Okay, yeah. So so what's happening is, so the main term looks like this exponent, and and then we have all these multiplicative error terms. And what happens, so this whole thing is actually what you get from one portion of the major arc at the origin. You don't even need to take the whole major arc at the origin in order to get all of this. And when you go to any other major arc, you're going to get something that looks like this, but you're going to get a slightly smaller coefficient in front of x to the 1 over k here. So you're going to get this exponent of something times 1 minus delta, say, times x to the 1 over k. And then once you have that, so if you have exponent of slightly smaller thing, then that's definitely smaller than this bigger coefficient times any power of y. And so that's what's happening, is that because we have this exponential main term, that the other major arcs are just incredibly smaller just because of how fast exponentials grow. Yeah?
So for the partition function, Rademacher wrote partition function as a convergence series.
Yeah.
Can you write, is it possible to give a convergence series for Pk?
So I don't know. I've looked at it a little bit. So I've written it in a way that it sort of looks like you could, if you could figure out what these coefficients are. So these coefficients are actually computable, but not easily computable. So in order to say, if you fixed some capital J and you wanted to say what these coefficients are, then they're going to be they turn out to be coefficients of certain polynomials that appear in the proof. And in order to compute, and there's some noise, so in order to compute, say, the first 3 coefficients, you would need to look, it would be like the first 3 coefficients of this 100-degree polynomial. So even the first 1 coefficient would be the coefficient of a 29-degree polynomial. So it takes quite a bit of computing power if you want to start looking at what these coefficients are. And so so I'm not quite sure what the growth is, whether this would converge. But if you could compute these coefficients and look at the growth of these, then it's possible that you could write it as a convergent series. But I'm not. I haven't worked out all of that sort of computer algebra sort of stuff. Oh, yeah?
You said you weren't interested in Warring's problem, but if you did fix the number of terms, could you get asymptotics for the number of ways of representing integers by, say, a quadratic form or something like that?
So I don't know using these. I haven't really looked at it. It's possible. I'm not sure using these methods just because I didn't encode the number of terms anywhere in what I was doing. So, so I'm not sure you would need. You might need some different method in order to do that. So I haven't looked at that. But yeah, that'd be interesting.
And so just to go back to the classical partition of P of n, so Hardy and Ramanujan showed that log P of n is comparable to square root of n.
Mm-hmm.
And so you can justify that by the circle method and looking at main term, major arc, and so forth. Do you know of any sort of heuristic, sort of more combinatorial way to see why log P of n is like is of order roughly root n that doesn't look at the circle method?
No, not off the top of my head. I can think about it, but I don't know right now.